Hey everyone, it's Ms. Butler. I got part 3 of the periodic trends video, and this one's all about the periodic trend called ionization energy. Just a quick recap, our goals is to define the trend ionization energy, compare and contrast like higher, lower ionization energy for two elements, and then we want to be able to know the pattern for ionization energy across a period down a group and be able to explain why. In case you missed the last video, periodic trends are just patterns that let us use the periodic table to predict a property or part of a personality of an element quickly without having to look up too much information. So we already saw a video on atomic radius. This video is going to focus all on ionization energy, the trend called ionization energy, trying to predict and trying to explain how it works. So the first thing we need to know is what the heck ionization energy is. And basically what it is we take an element and we put it in its gaseous state. It's not bonded with anything, and we remove an electron from that gaseous atom. And we want to see how much energy we have to put in to take that electron, to steal it away. When I say something has a high ionization energy, what I'm saying is that it takes a lot of energy to remove or steal that electron from the gaseous atom. So if I have chlorine, I'm talking about how much energy it takes to remove an electron from chlorine. How much do I have to put in to rip that away? Low ionization means it doesn't take a lot of energy. It's relatively easy, so to speak, to remove that electron. Okay. Remember, ionization energy is the amount of energy it takes to remove a valence electron from a neutral atom in the gaseous form. So what I'm talking about here, when I try to think about ionization energy, I think a lot about a robber stealing a purse. Maybe I'm a little jaded. I grew up in Chicago. It's not always the safest place. And there's definitely certain parts where you don't really have to worry about things. And certain neighborhoods or streets where maybe you hold on to your purses or put your hand over your wallet, put your backpack in front of you. Just you're more aware of the people around you. Okay, so when I think about a robber stealing my purse, if I hold my purse very tight, like tucked under my arm, really tight, I'm kind of squeezing it, that's making myself small, right? So if I'm the nucleus here with the P plus for protons, and I hold my purse really tight, the purse is going to be the electrons, I'm making myself small. So if a robber comes, it's going to take more work for him, right? He, as the robber, is going to have to put in more effort to steal the purse, which means it's a higher ionization energy. So if we're small, less rings, that means we have higher Coulombic attraction. When I say we, I'm talking about me with my purse, me with my electrons. If I'm small in size, I have high attraction to my purse, I'm holding on to it close to my body, it's going to take more effort to steal. If I walk around Chicago with my purse, swinging, there's the purse, right, swinging back and forth, my arms outstretched, right, I would look ridiculous, first of all, but that's not going to be very hard for a robber to steal, right, so that we say that that's low ionization energy, right, because the robber has to put in minimal effort. He can just pretty much walk by and knock that purse out of my hand. So if I'm an atom with lots of rings, big and fat, right, holding my purse way out big and fat, that's going to cause low ionization because I have less, I'm a big atom, low Coulombic attraction, which means low ionization, easier to steal. And then the other piece, what if I'm walking and there's another woman walking and we're holding our purse out normally, right? Not squeezing it tight to our body, not swinging it all around back and forth, but maybe equal distance. We're holding it like a normal person, maybe just on our elbow, right? The next piece, right, we have a tie for distance. We're both holding our purses out the same, but the next piece we're going to look at, if it's a tie for distance, is the number of protons. right? If distance is a tie, more protons equals more muscle. And it's going to be harder for a robber to steal the purse from someone who is like ripped and just came from Orange Theory versus maybe someone who looks pretty weak or scrawny, they're not holding on as much. Okay, same idea that we talked about when we did the atomic radius notes. So if there's more protons and there's more muscle, that means it's going to be a higher ionization energy. The robber's actually maybe going to have to do some work to steal the purse. They can't just yank it away. So here's the trend, right? This is the pattern or the trick to help us remember. As we go from left to right, ionization energy increases. So this means as we move, it's getting higher. And let's talk about why. As we go across a period, we have the same number of rings, right? The elements in the same row, they have the same energy level, but we add protons. As we move to the right, we have more protons, which means more Coulombic attraction, which means those electrons are kind of squeezed tighter to the nucleus. Someone's holding on tighter to their purse because they have more muscle, which means the atom is smaller, so it's harder to remove the electron. Okay, so this more Coulombic attraction means it's harder to remove, which means it's a higher ionization energy. As we go down a group, the ionization energy gets lower. Here's why. As we go down, this is the explanation you would put on a quiz or test. We add energy levels, right? So that means the distance between the nucleus and the valence electrons or the purse, right? The purse is getting held farther and farther out. The atom is bigger in size, low attraction. Basically, I'm like handing the purse because I'm holding it so far away, which means it's easier to remove that electron, which means low ionization energy. All right, so here's the little trick. As we go down a group, we are getting more rings added, so we're getting bigger and better. I'm holding my purse out, so as my purse gets farther and farther from my body, the ionization energy decreases, right? It's easier to feel as that purse is farther away. As we move to the right, we have the same distance, but we're adding muscle. We're adding more protons, so the person is holding on to their purse much tighter. So we get an increase in ionization energy. It's much harder to steal from helium than it is from hydrogen. It's harder to steal from argon than it is from sodium. So some things to keep in mind. Helium is the hardest to steal from. Big fat francium is the easiest to steal from. Here's a similar process. So here's kind of a typical question. Which has the highest ionization energy? Nitrogen or arsenic? Okay, so we want to do energy levels / number of rings, and then protons if necessary, of course. We're doing the same strategy that we did in the radius video. So let's see, nitrogen is in the second row, yikes, sorry, I'm making these videos in the summer, can you tell? Is in the second energy level, second row, and arsenic is in the fourth row. Okay, because these are not a tie, we don't need to look at protons, just like before. So basically, you have a lady holding her purse pretty close to her body versus a woman who's holding it far out. If we're looking for highest ionization energy, that's hardest to steal from. Hardest to steal an electron from. Who's it going to be harder or require more energy to take from? Someone holding it pretty far out from their body or someone holding it close? Well, it's going to be way harder to steal from someone holding the purse close. So here's our justification. Nitrogen in second energy level. Arsenic in fourth. Electrons closer to nucleus in nitrogen, so more Coulombic attraction. It's basically saying that nitrogen really likes its purse more than arsenic does. This means more energy needed to remove electron from nitrogen than arsenic. And now let's tie it back. You just showed me right here with this bullet point that you know what highest ionization energy means. Therefore, highest ionization energy is nitrogen. And now we answered the question. All right, I would like you to pause the video and try this one. We want highest ionization energy between sulfur or chlorine with a justification. So those black bullet points on the last slide, that's what you're going to do for this slide. So pause the video for me and try this one on your own. No, really, pause the video and try it. It's not a suggestion. All right, thank you for the two of you who actually paused the video and tried to solve this. So highest ionization energy, we're looking for most difficult to remove an electron. We notice that there's a tie in the energy level, so we have to look at protons, 16 versus 17. So here's my justification. Both of them are in the third energy level. Sulfur has 16 protons, chlorine has 17. Chlorine has more Coulombic attraction between the protons and electrons. This means that more energy is needed to remove an electron from chlorine because it has higher attraction, and that means chlorine has the higher ionization energy. All right, here's another question, a ranking one with 3 elements, or like a multiple choice, right? You're going to have sometimes more than just 2 options, so this is a good one to practice. We want highest ionization energy. We've seen that multiple times. That's the hardest to steal electron from. So let's make our little kind of summary chart. We have phosphorus, we have chlorine, we have bromine. We want the energy level, which is the same as the number of rings for us. And then if necessary, we need the protons. All right. Phosphorus, let's find that bad boy. Third row, third energy level. Chlorine, also third. Bromine is in the 4th. Okay, so right away I see bromine is standing out because it's different. Bromine is holding its purse like 4, arm lengths away. Chlorine and phosphorus, 3. So we know right away that this guy is the easiest to remove an electron from because its electron is farthest away. Okay, so this one is going to be the lowest ionization because it's the easiest. So we're going from lowest to highest. So right away, we know that bromine is the lowest. I find that students are bad at putting things in order. If that's you, like if you're like, do my alligator go like this, or does my alligator go like this, or do I do commas, like where are you at? My tip is like label it just like this. Whatever order you put them in, put some commas, and you can say lowest IE to highest, right? Just in case you're worried you're going to mix up what the question is asking. At least you're communicating to me, the teacher, you know which one's lowest, which one's highest. Okay. Now, since we already know bromine is the easiest to remove an electron, lowest ionization energy, I am not going to look at the number of protons because we've already ruled it out. So now we're just basically figuring out who's the highest out of phosphorus and chlorine. So phosphorus has 15 protons, chlorine has 17 protons. We have to look at protons just for these two because there's a tie for the energy level. So now let's see, well, if we're looking for the highest ionization energy, the one that's hardest to steal from, that's going to be the one with the highest Coulombic attraction. Or you could say the smallest one, same thing. Chlorine is going to be the hardest to steal from because it has more protons. So that's going to be chlorine, and then phosphorus will go in the middle. So my final answer is right up there. Hopefully this helps.